Because every data structure can be implemented in a variety of different ways, when we compare implementations, one important feature that we will consider is the relative efficiency of their operations. So in this presentation, we will consider a variety of issues related to algorithm efficiency and how it is measured. Initially, let's look at a few key points about algorithm efficiency. The first of those points is that when we speak of the efficiency of an algorithm, we must first clarify what resource we are measuring the efficient use of. There are two such resources that we will be repeatedly interested in. The first of these, and the one that will usually be of greatest interest, is CPU time. In other words, how fast the algorithm executes. Specifically, what we care about is how the amount of time required increases as the size of the data set grows. So you should envision that variation as a graph that plots the data structure's size on the x-axis and the amount of time required on the y-axis. The amount of memory needed is the second resource of interest. The efficient use of memory will be characterized in a similar fashion, which is to determine how much the need for memory grows as the size of the data structure increases. So next, let's think about how we can measure the efficient use of these resources. There are two fundamental techniques that we can use. The first is an empirical technique, which is much like an experiment we might conduct in science. This technique is more applicable to time measurements. It is often referred to as benchmarking. To benchmark the performance of an algorithm, we would run it on data structures of increasing size and measure the time it takes to execute. Then plot these data points on a graph and then curve fit that graph to characterize the growth rate. Unlike other sciences that measure the behavior in nature, programs aren't a part of nature, but something we have created. So there is another technique that we can use. It is what we will be using most often. It is an analytical technique. It involves looking at specific features of a program and, based on those features, drawing conclusions about the efficiency. One analytical approach we will examine is to develop a formula that counts the lines of code that are executed. Later, we will consider some simpler ways of analyzing the code to make this same determination. Once we have performed such an efficiency analysis, we need a way to compare the growth rates of various algorithms. To do that, we will introduce a notation called Big O that we will use throughout when characterizing the efficiency of the operations of a particular implementation of a data structure. Next, let's look at an empirical technique for analyzing the efficiency of an algorithm by counting lines of code. We will apply this technique once and then distill from it a somewhat simpler way to perform this analysis. The algorithm that we are using for this example is hopefully a familiar one. It performs a linear or sequential search of an array of integers, searching for some target value. The array and the target value are supplied as parameters. In our analysis, we are considering the worst case, which is that the value being searched for is not in the array. In this technique, we go line by line and determine how often each line will be executed based on n, which will represent the length of the array passed in as a parameter. In the first line, the subscript I is initialized, which only happens once. The while condition is tested n plus 1 times. Since the loop iterates n times, the test must be performed one additional time when the test fails, causing the loop to stop. Inside the loop, the comparison made to check if the target element was found is made n times, each time the loop iterates. We are assuming it is never found, so the return statement will never execute. So the count for this line is 0. Incrementing I is in the body of the loop, so it is performed n times. And the final return of -1 is done once, indicating that the target was never found. By adding together the number of times all the lines execute, we obtain a formula, specifically a function based on the value of n. What is most significant is the fact that this is a linear function. Of less importance are the coefficients involved. In the analysis of the linear search algorithm, we needed to consider the characteristics of the data supplied, because its behavior is sensitive to that data. Not being in the array is the worst case. If it were in the array, fewer lines would be executed, so the algorithm is data sensitive. It is often true that the efficiency of an algorithm is dependent on the data supplied to it. So let's return to our linear search example and consider the 3 possible cases which would apply to any algorithm. The best case is when the fewest lines are executed. In that case, only 4 lines would be executed, which is a constant amount. The worst case is the one that we previously considered. It is when the target element is not in the array. We concluded that the amount of time increased linearly with the array size. Finally, what is often of greatest interest is the behavior on average. For the linear search, if we assume the target is in the array, it could be anywhere. So we need to consider probabilities. Since it is equally likely to be in any position, on average, we would have to examine about half the elements. So our lines of code formula would involve n over 2. Although the number of lines would differ, it still would behave in a linear fashion. In some algorithms, like many sorting algorithms, the differences between the best and average case or the worst and average case are much more significant. As we mentioned previously, we need a way to compare the growth rate of the functions that characterize algorithm efficiency, and that big O notation is what we would use. To begin, here is a very formal definition of big O. This definition is used in performing proofs that a particular function is in the big O of another. Such proofs are beyond the scope of our discussion here. Nonetheless, examining the definition helps us get a better understanding of its meaning. Although many books will state that a function is the big O of another, the proper way to describe the relationship is to say it is an element of. There are a few parts of this definition worth noting. It involves 2 constants. The first is the constant c. The fact that we can pick c is what allows us to not be concerned about coefficients. In our formula earlier, we had 3n. n is what is important, whereas the 3 can be ignored. The other constant, n sub 0, is there as a way of stating that we don't care much about small values of n. We are more interested in what happens eventually for large values. Finally, the inequality states that all functions in O of g are upper bounds of f. Big O itself is a function, but it is what is called a second-order function because its domain and codomain both involve functions. The domain is the set of all functions. The codomain is the power set of all functions. In this form, all of this formalism leads us to what is of greatest concern to us, which is a way to order the growth rate of functions. Because we are dealing with sets of functions, what we have is technically a partial order. So the order is as follows. O of 1 constant functions grow the slowest because they don't grow at all. Algorithms with constant behavior are the best. O of log n is next. It grows, but so slowly it is almost constant. The binary search is an example of such an algorithm. O of n, linear, is next, followed by O of n log n, which we will see describes several sorting algorithms, followed by O of n squared, quadratic, and O of 2 to the n, exponential. Exponential behavior is the worst, and most exponential algorithms become unusable if n becomes very large. Although developing formulas by counting lines of code will provide a function that measures the growth rate of any algorithm, once we have used that technique on a variety of algorithms, we can distill the results into a series of rules for analyzing the efficiency of iterative algorithms. The first rule pertains to algorithms without any loops. All such algorithms execute in constant time, regardless of whether they contain any if statements. Next, we consider the case when loops are present. A single loop from 1 to n gives linear behavior. This is what we saw in the case of the linear search. Putting 2 or more loops in sequence will increase the coefficient, but we already observed that coefficients are unimportant, so loops in sequence are still linear. When we nest loops, that does change the behavior. A doubly nested loop gives quadratic behavior. A triply nested loop, cubic behavior, and so on. Finally, regarding memory usage, provided iterative algorithms do not dynamically allocate memory, their memory usage is always constant.